lot of words on this slide. I recognize this. Your exam has actual structures. It's just hard to get it all onto one slide. Yeah.
41.
41. We're always on 41. And I'll hit play here so you can make sure you can interact with the system. Who figured out how to move this last time?
1-5 diet, is that it?
How do you? I don't think I'm strong.
Is it 1-5 or 1-3? Dr. Dixon?
Yo.
Is that 1-3 or 1-5 diet for the cyclo?
1-3.
Ah, that's
1-3. 1-3. Just got dining is 1-3.
Is that it's dash 1-3?
Karate chop. Hiya!
Just see me and my brother when we were little.
Yeah, I see my son and my daughter. I'm sure it's about the same. 'Cause he has
1-3 dying.
Okay. So everyone can see that's 1-3, right?
1, 2, 3. This is 1 cyanoethane. Is that? Oh, Diels-Alder is when you have the diet, right?
Is that supposed to be ethene or is that really 1-cyanoethane?
It's ethene. It's ethene.
Okay.
Oh, it's ethene? Okay.
Here you go.
Thank you.
How'd you do? Now that we got this, we'll give you about 90 seconds.
Drawing group. So,
And we're done.
I don't know if it's, is it A?
Okay.
put
I
A.
think the answer is A. So give me
I don't know,
get
it's
that
smart.
right.
oh shit.
I don't understand why it's A.
In some ways, multiple choice is a good way to go, right? Sort of identify the products based on just the multiple choice answers. So if you're using that as a guide, good for you. You're learning how to take multiple choice tests, but the exam is in multiple choice. So A and D would seemingly be more correct than any of the others because of the placement of the cyano group, which you know has to be endo instead of exo, right? So this is the right placement, right? B and C, that cyano group is actually placed wrong. That pi unit should always be stacked underneath the alkene that's been generated in the Diels-Alder reaction. So by stacked underneath, I mean that this cyano group should be stacked below this pi system here. Now, while we diagrammatically don't see how that's stacking, when you actually look at the molecule itself with the proper bond lengths and angles and everything, it actually stacks just below. Whereas this is obviously out and on its own, right? So A and D would seemingly be correct, right? And perhaps you picked A because the OCH3 and the methyl are outside, right? And so they need to be in the same symbolism in the end product. Well, so they are both there. And then the geometry is such that OCH3 is actually going to be on top and the cyano below. So this is the right answer. But tell me how we're going to, when we attempt a question like this on the exam, how we're going to set about doing this. That's what today is about, right? Wrap up. We want to think about how to tackle these problems. We've talked through the theory, tons and tons and tons. So now you give back to me. How would I tackle a problem like this? Just start writing and pray? Is that what we're going with? It seems like there's so many. I don't know. Yeah.
Well, first you have to orient the two so that they can actually come together.
Okay. First, there needs to be an orientation piece, obviously. Okay. So this one's a little bit easier because it's a sigma bond. But say you had something like this, right? You would need to orient. Probably not the best way. You'd need to orient this into an S-cis configuration, right? So that the pi bonds of the diene are going to be moving or showing three-dimensionally toward now your dienophile, okay? And remember that the easiest way to do this, because you can think about how to rotate it, I have no idea why it's doing that, so we'll have to move on. Hopefully it'll work, but I don't know. In this case, you would need to maintain the right stereochemistry in here. This OH is on the same side, right? Is on the same side as this group here. So this OH is down and this CH3 is up. So sometimes that's an issue as well. But maintain your E and Z nature, your cis-trans sort of relationships must be maintained when you're just swinging around a sigma bond. okay? So that's A number 1 is to orient them right in this way. But the second orientation is to remember about resonance, right? Remember that you're always looking to generate a resonance negative charge on the diene that either is situated here or here. These are the two potential carbons that will behave as nucleophiles in the Diels-Alder reaction. Those are them. Those are the only two you want to focus on. So you want to question where that negative charge is going to be, right, when you draw your resonance structure. For this guy, the resonance structure is always going to be out here. There's going to be a partial negative charge out here if you look at all the resonance. You're never going to get a partial negative up here, okay? So this is where the negative charge will be. And when I orient now this other molecule, I have two choices, right? If I were to arrange this, I can either arrange it this way or I can arrange it this way, remembering that through resonance I have a partial positive charge, right, on the carbon the withdrawing group isn't attached to, would tell me that this orientation is not correct and the orientation on the right is correct. You see what I'm saying? Okay, one more time? Okay. Yeah. So in this case, going backwards, I need to go to the diene, and I need to draw resonance structures. I either want a resonance structure that puts a negative charge on this sp2 carbon or its tail end. These are the potential nucleophiles that are driving the reaction. Okay? So either here or here. Through resonance, if you draw the resonance structures, you should prove to yourself that never you're going to get negative charge when the OCH3 is there. Alternatively, if you want to see an alternative, if I put the OCH3 here, okay, and the methyl here, this would drive negative charge here. Okay? See if you can't, through resonance, prove that to yourself. Okay? But in this case, it's going to drive negative charge to this carbon down here. Okay? So I need to focus on where it's going to go. Then I need to do the same thing on the dienophile. So I have to say, in my dienophile, when I draw resonance structures, where's the positive charge going to be? Positive charge is always going to be on the carbon the withdrawing group is not attached to. So now, when I orient them, I have to either have the negative charge and the positive charge both on the bottom or both on the top. Okay? Both on the bottom or both on the top, right? Everyone see that? Are we with me? All right, good. So then when I go to draw the Diels-Alder product, these are driving me crazy. When I go to draw the Diels-Alder product, then I know this is my orientation, and hence I come through to draw the product. I tried to make it a little bit easier for you. I know that these are very hard for you to see, these types of rings, right? So I tried to make it diagrammatically easier for you to see. But I know that my OCH3s here, right, are going to be, and my CH3 here, they're going to be on the same side, right? So you need to have some symbolism that they're on the same side. I know they're on the same side because they're both pushing away from the diene, right? Remember what we said when we had an open diene, that these guys always wound up in the same position, right? Same symbolism, and these guys did three-dimensionally. Okay, so they have to have the same symbolism, and where the cyano group is going to be is down here.
What?
Okay? Yeah. You have to have the right stereochemistry, the right regiochemistry, and all the rest of that for to assume you did the problem the right way after that. I mean, we're not going to be looking for you to work through it stepwise. I'm trying to just remind you of what the theory is and how to set it up. But no, we're going to be grading you, though, just like we did on the homework, based on you drawing a Diels-Alder adduct that has the right regiochemistry, meaning the right constitutional isomer where the attachments are, and the right stereochemistry. Okay, so if that's met, then you're totally good to go. Yeah.
It seems to me that it just looks like the cyano group would be on the rear carbon.
Oh, yeah. I'm sorry. I looked at this diagram. The one I X'd out. Bad me. You're right. I just looked right here. I looked to my left. Did not even look at the X on it. My bad. Gotta get on it. Okay, are there more questions? Yes?
Was that answer A or answer?
Oh, I don't know. So now that goes back to the question of what it is, because I have no idea. Hold on. Let's get out of here. So this answer, the OCH3 has to be A. No, D, right? No. Sorry. It's gotta be A. My bad. I gotta get on it. I'm gonna get on it. I swear to God, I'm sweating up a storm up here, though. I feel like I'm gonna pass out. It's like, yeah.
No, it's gotta be
Go ahead.
D.
Why did you
Because it's going to be one bond away from OCH3, and that's what it is. There's two bonds away from OCH3.
So it's not equatorial or axial, although I get that it looks axial. Yeah.
It should
So
be
there's
D.
two potential products, and they're both shown there. So if you compare, guys, if I compare A and B, right, it's always going to look axial in your Diels-Alder adduct, and the reason for that is the pi stacking, which is actually a driving feature. So if you actually built a model of this, that pi bond on the cyano group would sit below the pi bond created in the Diels-Alder reaction. Okay? Yes?
So is the answer D? Or-
No. So the answer is that the OCH3 and the cyano here. So if we were to draw it like this, right? I can't even do it. Okay, hold on. Here we go. Okay, so this is what I have, right?
Yeah.
My OCH3 is here. My CH3 is here,
Right.
which means now my cyano group, right, has to be on this guy down here, right? And it has to be down on this guy. Now my OCH3.
It's supposed to be two bonds away from the CH3? One bond away from OCH3? I'm confused.
I don't think you have the right answer.
I put the cyano group right on that as opposed to, yeah. So here's the issue. I see where you're having issues. So this is still 3 carbons, right? That's 3 carbons. This is still 3 carbons. This is carbon 1, this is carbon 2, and this is carbon 3.
Yeah.
There's only 3 carbons. This is right. We can talk about it later. I don't want to take any more class time for this. I'm telling you that we're good to go. The diagrams just look differently. Okay. If you want to talk about it more, I'm happy to talk about it more, but we got a lot more to do. Okay, so I'll draw this structure up because this seems to be causing you trouble. 4-methyl-1,3-diene, I guess a pentadiene here, reacts with HCl. Choose the most stable carbocation that can form. I'll draw this up very quickly so you can see it. Okay? Does everyone see that even though the projector's still on? I can't turn the projector off because the computer doesn't work. I'm just going to move it down so I don't have to work over there. It's over here now. And we're done. Yeah, I thought that you'd all fall for that. The answer is B.
Neither should we not.
I knew it.
The answer is B. I can't tell you enough. So here I am again, and this time I'm screaming. Do you hear me? All right. The alkene that reacts first is the more substituted alkene. Which one reacts first? More substituted. Okay, that means that now, if I'm to look at this, this is my reaction. I have only one intermediate that I'm interested in here, and that's this intermediate. This intermediate because it's allylic. It's secondary allylic, right? The one that doesn't form is this guy here, right? This is a no because it's only tertiary. Only tertiary, okay? So you're all getting this stepwise process wrong. The theory is such, if you follow it down to the nitty-gritty, that the more substituted alkene reacts first. So that's the first thing I do. I decide which alkene has more substitutions on it. That's the one to go. And I always create the allylic carbocation. Always creating the allylic carbocation. And now I have a resonance structure that exists simultaneous, right? The resonance structure here is this resonance structure, which creates this carbocation. And I have a way to discern between kinetic and thermodynamic products. Which intermediate is my kinetic product? The first one or the second one? The first one. So how would I run this reaction? I would run it as low temperature. Exactly. I would run it at low temperature. Okay? All right. So, moving on. Make sure you can do those. You guys always fall for that. But don't fall for it on the exam, please. Okay. Determine if these structures are aromatic, anti-aromatic, or just not aromatic. Aromatic, anti-aromatic, or just not aromatic? Three, two,
Because
one,
C is definitely just not aromatic.
Okay, that's actually right.
Good.
Good. Good. All right.
What's going on with
Now
N?
let's just one up the question. Ready? So I'm going to use, this is where I can use this.
Good.
You like that? Everyone see that? Okay.
Let's get a
Let's
hydrogen
play
on
the
it.
game of where does the electron pair reside? Okay. So I have two electron pairs here. Where do they reside?
One's inside.
You want to
one's
know what
out.
your choices are?
Sure. Yeah.
Asia, Africa, a p orbital or an sp2 orbital, right? These are your choices. A p orbital or an sp2 orbital. I guess technically they can belong in an sp3, but we'll go with sp2 or p. So, what do we got here? One p and one sp2. That's exactly right. Only one of these electron pairs resonate, right? Only one at a time resonates. So if I choose this one, say, to be the one that resonates, that can make a pi bond to the neighboring atom, it then automatically resides in a p orbital. The minute an electron pair can resonate, meaning it can donate an electron pair, right, it's going to be in a p orbital, all right? So one of them is in a p orbital, and the other then belongs in the sp2 orbital, okay? How about this guy here?
P orbital.
It belongs in a p orbital. Okay? That belongs in a p orbital. And how about here? We have two electron pairs over here. P and sp2, right? Same thing, one in each. Because one of these electron pairs can resonate. Even though the system is just not aromatic in the end, right? One of these can resonate. So I have a conjugated system here in this molecule. Does everyone understand what I mean by that?
Yeah.
Yes? Okay. Let's just, before we go back to clicking here, let's just answer one more question on aromaticity. So, or actually, just a couple more things I want to say about aromaticity. So here are two systems. Yeah. So let's do this one and I guess this one. So these are two acidic protons. So we can play this game. On my last year's exam, actually, we can sort of play the game even better. On last semester's exam, I had a little Y here. And I said, if Y is actually a hydrogen, the question is, which one is more acidic? So if Y is a hydrogen, which one of these molecules is more acidic? So the way that I would answer that question is I take off the Y, I would replace it with a hydrogen, but I know to consider the acidity, I would actually need to put an electron pair back here, right? When the hydrogen is pulled off to create its conjugate base, it leaves behind an electron pair on that atom. So now I would question, which one of these then is more acidic? Is the first molecule more acidic or the second? The first. And why is that?
Stronger conjugate
Because
base.
it creates an aromatic, right, ion. Okay, it's nothing to do with resonance. Make sure you have the language right. I have a choice between creating an aromatic system or an anti-aromatic system. An aromatic system is always more stable than an anti-aromatic system, and just in between those would be the just not aromatic category, right? Of which neither of these fall into that, but I'm just saying.
There's the hydrogen on them, right? On
There
those couple.
was, and then I said we're going to remove the hydrogen and look at the stability of the conjugate bases.
There's another one on there as well.
Oh, yes.
Okay.
Okay, so in this case, if Y is Cl, the question on the exam was, right, so we go back and look at, if Y is Cl, so I guess I'll, instead of Y, I'll put the Cl there. Which one of these is faster in an SN1 reaction? Okay, so in this case, I would rip off the Cl, and I put in its stead a positive charge, second one is faster, right? The second one is faster because in this case, the carbocation version of this is aromatic on the right and anti-aromatic on the left, right? When I look at these cations, this guy is aromatic and this guy is anti-aromatic, and hence, now I know that aromatic is more stable, and we're always interested in carbocation stability, right? Now, could you prove to me with MO theory which one of these is more stable?
The
The
left.
answer is yes. I would use frost circle, and frost circle requires that I put a vertex down, right? So we go back, and we just take these shapes, and I make frost circle here. My pentagons are always terrible, but I can tell you that these are all bonding. I'm not very good at drawing pentagons freeform, nor inscribing them in circles for frost circle, but I'm telling you that these are bonding, these three. And then you have two anti-bonding, right? Because this is what you do. You take the shape, vertex down, you inscribe it in a circle. If you're very exacting about it, and you shade half the circle, you see the part that's shaded is either bonding or anti-bonding, depending if it's down or up, and the other half would be the opposite. So what I would find in my circle is that these would come right below the non-bonded line. So these two here are actually bonded, okay? If you were very exacting about it, you'd see it. Now, if I look over here, this one's a little bit easier to inscribe and to agree that there's only one bonding, right, MO here. So my dividing line here, I guess, is right here between bonding and anti-bonding. Okay, does everyone see?
Is it anti or non-bonding?
So now what do? So all I've done is make the MOs, but you haven't proved anything yet. So what do I do now? I fill them with the proper number of electrons. Great. There's 2 pi electrons in this system, and there are 4 pi electrons in this system. So I'm correspondingly going to go add the 2 and the 4. So here we go. So I'm 2 into this system, right? They both go into this because I put 1 in and then I spin pair. This guy's going to go 1, 2, 3, 4. So how does this prove to me? What would be the 2 situations that would prove that the guy on the right now is anti-aromatic? Nope, we're using MO theory. What about this picture tells me that that's an anti-bonding? Yeah.
Because the one on the right has unfilled orbital, has partially filled orbital, and the one on the left has a full orbital, so it'd be more stable.
That's exactly right. So if I see any radical character, which are single unpaired electrons in either bonding or antibonding, it doesn't matter, that is not a good sign, right? That is a sign of an unstable system or an anti-aromatic system. The more obvious one is if you fill any electrons into the antibonding, right? That would be the more obvious case. I chose a less obvious case to make sure you know there's 2 cases with MO theory that dictate it being anti-aromatic. This is one of them, when I only have partially filled bonding orbitals. And the second case is when I fill into the antibonding orbital systems. Okay? Does everyone understand these types of questions? Okay, great. Let's move on then. So, we keep going here. This system is desperate to get me on the web. Desperate. All right, which reaction gives acetophenone as a product? Phenol with KMnO4, styrene reacted with H2O2H plus and KMnO4, or styrene reacted with Br2, excess NH2, and then KMnO4.
What's acetophenone? Isn't that just like the Yeah.
Is that?
It's what?
Because it's kind of tautomized.
Yeah.
So.
One.
I don't know the terminology, but I'm looking for a straight chain.
Okay, the answer is C.
High five.
We're both too lazy. We're like, high five. Level 1.
Actually, I'm finding an issue with this slide, but the lesson here is one that you all forget about. Every slide has an actual lesson to it, as you can hear me screaming at you. It's day of screaming. And that is that if you have any benzylic protons, right, KMNO4 is not going to give you anything but benzoic acid. Okay? So be very, very careful. But first is a distractor. A is a total distractor, and that's not going to do anything. So it might form some quinones, which you may see in your electron chain reactions, right? Down at, no? Anyone know what I mean? You know, creating energy, moving hydrogen against the gradient to create ATP and ATP synthase. Anybody? Most interesting protein ever, ATP synthase. Seriously, that's a fascinating thing. Do you ever see the structure of it and how it works? It's the most amazing thing ever. Anyway, so that's the lesson for this slide. We're running out of time here, very fast here. So let's rank the following in terms of reactivity with NaOCH3. Note there's no heat present. That should tell you something vital.
It's not going to go to
1, and we're done. Okay, so I think the answer is C, but let's look at this. I think. Hold on. So A is O-nitrochlorobenzene, so that's this guy. This is A. So this will do a Meisenheimer complex. That's a yes, right? So that'll run a Meisenheimer complex. It's a requirement to have an O and P nitro group, right? So this will definitely run quickly. It'll go through a Meisenheimer complex. No heat is involved, right? So that's my only choice is a Meisenheimer complex. I look at B, and that's 3,4-dinitro. So now I have 2 electron withdrawing groups on the ring, and one of them is para. So if I just had the para, that would be equal. But since I stuck another electron withdrawing group on the ring, right, this is going to go faster. So this is going to go through a Meisenheimer complex, and this guy is going to be faster. And correspondingly, since I only have a 2-point comparison, this guy's going to be slower because B has 2 withdrawing groups on it, right? So it's really primed better for nucleophilic aromatic substitution, okay? The last one is an M-nitrochlorobenzene is not going to do a Meisenheimer complex. I have no heat present, right? So my only choice of nucleophilic aromatic substitution is a Meisenheimer complex. So this is no Meisenheimer complex, so this for sure now is going to be the slowest, right? So what number is that?
B.
B, thank you.
Better.
It's what?
B.
I said, I don't know the answer, just relax. I don't memorize the answers, it's not like I have it up here in my memory. Okay, there are questions about this guy? So the
Why is
fastest
the
one
last one,
is
it
B.
doesn't do Meisenheimer?
It
In
needs that
between
OP.
is A, followed way behind, right? Maybe not even reacting. There should be a whole bunch of less than signs. C. Okay, does everyone remember what I said about these 2 last class? These are also comparing
I'm leaving it to
Meisenheimer versus benzene. Okay?
I'm out of
Which one of these is
3
going to
minutes
undergo a Meisenheimer complex intermediate? The reaction on the left or the one on the right? Okay, great. So when that NH2 reacts in a nucleophilic aromatic substitution, how many potential constitutional isomers do I get out of that reaction? 1. I get 1 constitutional isomer, right? The only constitutional isomer I get is this guy here. As there's a direct reaction here. How many constitutional isomers do I get here? 3. 3 constitutional isomers, right? Because it goes through a benzyne intermediate, right? So this is one potential benzyne, and this is the other potential benzyne intermediate that it can go through, okay? Which means now I can get substitution at this carbon, or from this one, this carbon, okay? So I have 3 potential constitutional isomers. Please remember that the difference between these reactions is as such. That's sort of a helpful hint when you're looking at, these large reaction webs. Okay? Are there questions about this? Everyone understand what I'm saying? Okay, if you don't, come on by. So I know I'm going fast here. All right. Next up is this one. I am going to give you a little bit of time to think about this. This is the last quicker question today, and then we can do some synthesis and talk about the exam.
What's more likely to happen, my dear?
2,
Or
1,
D. I put D.
and go.
Oh, wow.
Good job.
That might be right. in terms of which ones are going to have pKa's to the right of aniline, or the conjugate acid of aniline, this will be a higher one, right? And this will also be a higher one. So D is going to be the highest, though, right? Followed by A. Those that are going to track with lower pKa's, meaning to the left, more towards 0, are going to be the cyano and the bromo. The cyano is a resonance, right, relationship or explanation, and the bromo is an inductive, which means this is going to be BC. So what did we do? That's D. And you got it. A lot of you got it. Okay. So let me remind you, because we've been talking about this a lot. Okay? Let me remind you about trying to get you to use a very thoughtful process as you're answering these questions, right? The first is to separate them into electron donating groups and electron withdrawing groups, right? So that's the first thing I did. I went to the electron donating groups and I sort of checked them out, right? So I have 2 that have electron donating groups, A and D. So then I consider, are these electron donating groups an inductive effect or a resonance effect? I remind you that an inductive effect are really all those R groups, right? And a resonance effect are all the strong and moderate activators, okay? If the activators are in an OP relationship, that's the wildest and most extreme effect, and those will be the least acidic, okay? I didn't have any comparative, I didn't have any inductor or resonance at meta positions, but the OP should win out. You won't ever be asked to distinguish between an O and P resonance contributor, okay? So D came out here, A was next. I followed here by then going to look at the withdrawers and doing the same thing. Are they resonance effects or are they inductive effects? The resonance effects are going to have the largest effect on the pKa. But in this case, they're going to be the smallest pKa, right? They're going to make something even more acidic if they are O and P placed, okay? So this is the order here. You're looking for practice problems like this, which you should be, because this is about 10% of your exam. 10%, okay? That makes it a how many point problem? 15. There are practice problems on the weekly quiz, okay? All right. This is pretty much what I have to say today. Are there questions left about the material? Okay. There's a couple questions, and then I'm going to tell you the framework of the exam. So go ahead. Oh, geez, the photo's still not up there. My bad. Okay, I have a photo. I will put it up right away. Sorry about that. Okay, so I have a JPEG of the answers to the web from, I think I did put it up there. Yeah, it is. Okay, I'm like, I can swear I'm not losing my mind. You've seen it, right? Okay, thank God. I'm like, because it's either that or I'm really gone. All right, so here's the framework for the exam. There is a large reaction web. It's about 40 points. Make sure to work forwards and backwards. Don't just start at the center at one end and try and prod your way through, right? And sort of push your way through. Go and look for reactions you can do. Don't just start in one place and work in one direction. That's not going to help you, okay? There is a couple mechanism questions on the exam, okay? One of them is very straightforward, extremely straightforward. And the other is a thinking problem. So you're going to need to put your thinking cap on, kind of like the homework problem from the last homework set. Okay? So past that, there's a spectroscopy question that's embedded in synthesis. So you solve for the molecule, you'll get a large amount of points. If you can show me how to synthesize that molecule, you're going to get a few more. Okay? And then after that, it's basically open to what we've been covering, which includes MO theory, right? 1,2,1,4 products, Diels-Alder, electrophilic aromatic substitution, nucleophilic aromatic substitution. The problem I promised from class a couple classes ago is there, and it is actually problem number 1, as I promised. Okay? Does anyone remember last week, on this right board here that's now behind the screen, I made a big deal about making a table, and I called out things, and you said to me where to put them in the table? And I promised you something like that would be on the exam? Yeah, it's there, okay? So you really need to know what an electron donating group is and an electron withdrawing group, Okay? Here's something I can promise you. Number one, there's no nomenclature on that exam. I know the clicker questions abound with them because there's only so much I can get into one slide, okay? But there's no nomenclature on your exam, okay? And number two, as promised in class, you can acylate or alkylate a halogenated benzene. We will allow you to acylate or alkylate a halogenated benzene. You will lose points if you try and do that with a moderate or strong deactivator on the ring, okay? If you have other questions, I'm happy to answer them. Kim will be in discussion tomorrow. Good luck. Be on time because we start on time. If you're late, you lose time.